This is part 2 of our last lesson on nuclear chemistry. We're going to focus on radiation exposure, which means the sources of radiation exposure and also some of the health effects from being exposed to radiation. And then we're going to focus on some positive ways that we can apply nuclear chemistry for good. So sources of radiation exposure, y'all, I see a lot of them here, okay? There are many sources of radiation exposure. One thing I want y'all to notice is that a lot of these sources are kind of categorized also as background radiation, which we will get into here in a second. A lot of these categories are also classified under medical. We know medical technology and imaging can be done for good to let us see stuff inside of our body and diagnose diseases, but those are also a potential source of radiation exposure. Also down here, I have some consumer, industrial, occupational sources as well. Now, let's talk about background. Background is exactly what you think it is. It is stuff in the background that we really cannot do much to prevent, okay? And the ways you can get background radiation are from a lot of places here. Cosmic radiation is coming from space. I can get background radiation from building materials. Background radiation can come from the soil and rock underground. I can have some level of background radiation in the food we eat. And even wildly enough, is you can have a certain level of very small, but background radiation coming from your internal body processes. Okay, now in the soil and the rock, here's an example of some source of background radiation. Uranium-238 in the soil actually, unfortunately, decays into a very carcinogenic gas called radon-222. So there is a potential monitoring that we have to do to make sure that decay into radon gas is controlled within our houses. Now, another source of radiation is a particular type called ionizing radiation. Not all radiation is ionizing radiation, but ionizing radiation is a type of radiation that produces harmful free ions in the body. We see this a lot with x-rays, medical x-rays. Now, the way ionizing radiation works is it creates harmful free ions that go on and do pretty bad things in your body. What I mean by creating harmful free ions is that it removes electrons from the atoms in our body, and then we have atoms that now exist as ions, and then they do not behave the way we would want them to. So medical x-rays do provide a significant amount of ionizing radiation. Now, the last two categories of sources of radiation exposure are not anything that we should be worried about, meaning the contributing amount that they contribute is very, very small, but I find that kids are very interested to learn about nuclear weapons and nuclear power plants in terms of what does that mean with radiation exposure. So with nuclear weapons, there is testing of atomic bombs and hydrogen bombs. And as a result of that, you can create harmful radioactive particles, okay? Now, the bad thing about this is the radioactive products of these testing events, they have a really long half-life. We've talked about half-life before. That just means that it takes a really long time for those dangerous radioactive particles to go away. They can be found in the atmosphere and in water sources many years later. Now, these radioactive particles, if they're being found in water sources, they can then get into the food chain and become biomagnified. Well, what is going on? Like, what is the timeline here of the nuclear testing that we have done so far in history? Well, it obviously all started with World War II when we dropped the 2 bombs on Japan, okay? Keep in mind those bombs were atomic bombs, which means they were fueled by a fission reaction. Since then, the nuclear weapons that have been pretty much strictly created and tested have been hydrogen bombs, which are fueled by a fusion reaction, which is much more powerful. As you can see, there's a kind of a big uptick in the amount of testing that was done worldwide in the 60s, and that was as a response to the Cold War. But we have not since World War II deployed any nuclear weapons in warfare. Now, in terms of the radioactive particles that are produced from these nuclear weapons, they can get biomagnified. So what that means is if I have some particles that are in the water, then it gets magnified up the food chain to where it becomes more and more concentrated and becomes more dangerous. Now, the last thing I want to focus on are nuclear reactor failures. We know nuclear reactors run by a controlled fission reaction, right? If that fission reaction becomes uncontrolled, then I can get that really aggressive, very dangerous chain reaction, okay? So there have been some nuclear reactor failure events throughout history. These are not a scary source of radiation exposure unless you are site specific to that area, which then it was extremely important. So we're going to talk about the the big three nuclear reactor failures that are the most prominent in terms of danger and eventfulness in history. So Chernobyl happened in Ukraine in 1986. It's known as the worst nuclear disaster accident in history. What happened was it was a flawed reactor design that was combined with operation errors during a safety test, and that caused a catastrophic explosion in reactor number 4, leading to a meltdown. The radioactive fallout was more than 400 times greater than the Hiroshima and Nagasaki atomic bombs combined. So we are talking about a significant level of damage. Let's learn more about Chernobyl.
The world's worst civilian nuclear disaster took place when a reactor exploded at the Chernobyl power plant in Ukraine, then part of the Soviet Union. Present-day Belarus received 60% of the initial fallout. The radioactive cloud spread further to cover most of Europe. The Chernobyl nuclear power plant was one of the Soviet Union's most advanced facilities. The first 2 reactors became operational in the late 1970s. The 4th reactor was the newest, going online in 1983. On April 26, 1986, technicians prepared to test the backup cooling system in reactor number 4. But the routine safety drill went horribly wrong. A nuclear reactor is like a giant steam engine. Uranium fuel rods react to produce a massive amount of heat. That converts water into steam, which drives huge turbines to generate electricity. Control rods are inserted in between the uranium to slow the reaction. And it's crucial for cooling water to be pumped around the core to prevent overheating. But as the test began, almost all of the control rods were removed, and technicians lost control of the flow of coolant. Temperatures soared, and extreme heat began to melt the core. At 1:23 a.m., Reactor 4 exploded. It spewed 8 tons of radioactive debris into the atmosphere. 115,000 people were evacuated from a 30-kilometer zone around the plant. The battle to put out the fires inside lasted for 15 days. More than 500,000 military and civilian personnel were drafted to deal with the accident and its aftermath. 31 of the initial firefighters and plant workers died within days from acute radiation sickness. The toxicity of the radioactive cloud was equivalent to 400 Hiroshima atomic bomb explosions. Crews hastily built a concrete sarcophagus to encase the entire reactor to prevent more radiation from spreading. Inside, there remained 200 tons of radioactive fuel. The remaining 3 reactors continued to operate due to energy shortages in Ukraine. It wasn't until the year 2000 that the Chernobyl complex was completely shut down. With the concrete sarcophagus crumbling, the international community began to build a new confinement structure for Reactor 4. It stands 110 meters tall, higher than the Statue of Liberty, and it's wide enough to fit a ship the size of the Titanic. At a projected cost of $3 billion, construction is scheduled for completion in 2017.
So we're talking a significant amount of radiation that is still coming off today from the source of that nuclear reactor failure. The construction of that concrete sarcophagus that was projected to be completed in 2017, that's a real interesting story in itself. So let's look more into that.
This was a very long project. We have started here in 1998 with lots of preparatory works that were required, studies, Some infrastructure had to be provided. The contract for the new safe confinement was placed in 2007, so this is already 12 years ago. That's the time it took to design and construct the facility that you can see behind me.
Которые находятся в непосредственной близости от аварийного четвертого, тоже выводятся из рабочего режима. В его помещениях сейчас осуществляется...
So with the construction of that concrete sarcophagus, they had to construct it off the site of where the reactor was because to protect the workers from the harmful radiation that was still coming off of the reactor. So this is going to be a constant thing that will have to be monitored for probably a very, very long time. Something that's kind of interesting about that reactor disaster is this thing called the elephant's foot. And this was that large mass of corium and other radioactive waste material that was directly underneath reactor 4, okay, that came from that nuclear reactor meltdown. And it was thought to be the most radioactive object in history. It's a little bit debatable, but a lot of radiation was coming off of what is known as the elephant's foot. And I think it's called the elephant's foot because it looks like an elephant's foot. So Chernobyl was by far the worst nuclear power plant disaster in all of history. The second worst one happened in Fukushima, Japan in 2011. Now, this was triggered by a 9.1 magnitude earthquake and a resulting 132-foot tsunami. The Fukushima Daiichi plant experienced a meltdown in actually 3 reactors. The earthquake and tsunami disabled our backup power systems and it prevented the cooling that would have led to keeping it under control, and it also caused hydrogen explosions on site. Let's learn a little bit more about Fukushima.
The Fukushima Daiichi nuclear plant has 6 reactors that were all built in the 1970s. They're old designs, but they were considered pretty safe. On March 11th, a magnitude 9 earthquake struck off the coast of Japan, and the earthquake was obviously bad, but the tsunami it created was what really caused trouble at the plant. Right after the earthquake, the reactors went into emergency shutdown, and they needed to be cooled. That job was being done by generators, and the tsunami came in and washed around the reactor buildings and just knocked out all those emergency systems. So without the cooling systems, the 3 reactors running at the time of the quake began to heat up. Plant workers scrambled to flood them with seawater, but it took too long, and it appears that the reactors partially melted down. Now that means that some of the fuel inside got out of its normal configuration and possibly settled at the bottom of the reactor. The process generates a lot of hydrogen gas, and that sparked a series of massive explosions at the plant over the next few days. Now, after the explosions, all that mattered was keeping these reactors very cool. Japan's military and civilian authorities did really the only thing they could at the time, which was spray water. Over the last month, the water spraying has gotten a little more systematic, and damage assessments have begun. It hasn't been easy because the radiation levels are just too high for workers to go in and look at what's happened. So what they've had to resort to is unmanned helicopters that can sort of provide an aerial view of the damage to the buildings that house the reactors. Remote cranes have also given us a look at the tops of these buildings. But what reactor operators really need to do is take a look inside. And to do this, they've turned to robots used by the U.S. military. The robots first entered Units 1 and 3 in early April. What they found wasn't particularly encouraging. As we suspected, the radiation levels are still very high. So basically, these reactors are going to have to be cooled remotely, at least for the next 6 months or so. The cooling creates another problem because water that goes into the core comes out contaminated with radioactive material. It flows out through broken pipes and cracks, and it can eventually reach the ocean. The Tokyo Electric Power Company has spent a lot of time trying to seal the leaks one way or another. Some of their techniques have been pretty crude. I mean, they've just filled this pit with concrete. TEPCO is also planning on pumping the contaminated water into temporary storage tanks, and at least trying to process some of it to clean it up. Over the next few months, the damaged reactors will also have to be covered to prevent radiation from spreading. TEPCO says it wants to build a temporary cover over the site. It could look like this one that's currently being built for Chernobyl in the Ukraine, although there it's taking well over a decade to install. Up until now, people on the site have just been focused on keeping these reactors under control. It's been a 24-hour job, and they haven't had much of an opportunity to get beyond that. But ultimately, they're going to have to figure out a way to get the fuel out and take the reactors apart. At the moment, nobody seems to have an answer for how to do this, but we're likely to see more ideas in the weeks and months ahead.
So the reason why these reactor failures are called disasters is, as you can see, it's not just like a one-time event and then it's done. The radiation fallout from these disasters is significant and long-term. All the more reason for us to really focus our science on trying to hone in fusion-powered reactors and seeing if we can come up with that. The first very major nuclear disaster happened on 3 Mile Island in Pennsylvania in 1979. And what happened here, it was a partial meltdown, and it occurred in reactor 2 due to a relief valve failure following just an unplanned shutdown. Radioactive steam was released, but no immediate injuries or discernible health impacts were reported. The most important part of this accident was it just highlighted the importance of public communication and nuclear safety. The public was not being given information, and they were being confused, and it led to kind of a little bit of an outcry. So here's some news footage of when 3 Mile Island disaster actually happened.
It was the first step in a nuclear nightmare. As far as we know at this hour, no worse than that. But a government official said that a breakdown in an atomic power plant in Pennsylvania today is probably the worst nuclear reactor accident to date. There was no apparent serious contamination of workers, but a nuclear safety group said that radiation inside the plant is at 8 times the deadly level, so strong that after passing through a 3-foot thick concrete wall, it can be measured a mile away. Gary Shepard reports from Harrisburg.
The accident occurred here at the 3 Mile Island nuclear power plant a dozen miles south of Harrisburg. At about 4 o'clock this morning, 2 water pumps that help cool reactor number 2 shut down. Officials say some 50 to 60,000 gallons of radioactive water escaped into the reactor building, and that the radioactivity penetrated the plant's walls. Steam escaped into the atmosphere, and radiation was detected as far as a mile away. At least 50 workers, and perhaps twice that number, were at the plant when the accident occurred. A spokesman admitted that some were exposed to radioactivity and may have been contaminated, but he claimed no one was injured. All workers were given extensive checks with Geiger counters as they left the plant. Reporters were not permitted inside the facility today, but this is what reactor number 2's control room looked like last September when it was still undergoing testing. It went into commercial service only 3 months ago. Officials from Metropolitan Edison Company, which operates the plant, attempted to minimize the seriousness of the accident, saying the public was never in danger.
We may have some minor fuel damage, but we don't believe at this point that it's extensive. The radiation levels at the site boundary are really only a tenth of the general emergency level where we normally get concerned. We do have our crews out. We're monitoring for airborne contamination. The amount that we found is minimal. Very small traces of radioactivity have been released from the plant.
But the company's statements have not answered several important questions. How much radioactivity has already escaped from the plant? How high is the radiation level inside the plant? And is there still a high level of radioactive steam inside? The Nuclear Regulatory Commission has already begun a complete investigation into today's accident. Power company officials say it will be weeks, perhaps months, before reactor number 2 is back in operation. Gary Shepard, CBS News, Middletown, Pennsylvania.
So it's a pretty significant thing if the communication is not honest and immediate to the public when a situation like this occurs. But luckily, these situations where there's nuclear reactor failures or disasters are very few and far between, but they can be potentially disastrous. So there's got to be some health effects of this radiation exposure. And yes, there is. The main kind of overwhelming source of the reason why we experience health effects is that radiation actually comes in and it damages your DNA, causing either cell death or DNA mutations that can either pass down through cell replication and then onto your kids potentially. Lots of other things like skin diseases, cancer, radiation sicknesses, lung problem, like a bunch of different stuff. Radiation turns out is not good for you. But we have ways we can detect radiation. Geiger counters actually pick up levels of radiation, which lets us know what levels are appropriate or not, meaning how safe they are. Also, medical workers will always wear these film badges, which lets them know their own exposure to radiation. We know in the medical industry, there are a lot of radiation imaging techniques that are used for good, but it also is important to kind of monitor the exposure that medical workers may be receiving from that. So what's the most terrifying word in nuclear physics? Oops. Okay, so now let's talk about some good things that can come from nuclear chemistry. Okay, there are a lot of wonderful applications in nuclear chemistry. We talked about the medical industry having a really, really good idea of what we can do with some of this for good. So radiation therapy is a very common therapeutic method for us to target cancers, right? So we can use gamma and X-ray radiations. Cobalt-60 creates gamma rays that can go on and target site-specific tumors and help kill them without destroying other things going on in your body. Proton therapy is a new type of therapy where I can actually use proton beams and they are targeted at a specific cancerous cell part, and you're not going to get this like background blast effect like you would if you were using X-ray radiation. Okay, the proton therapy just tackles that really small site where the tumor is actually there. There are in medical technology radioactive tracers. Radioactive tracers are non-ionizing and they're absorbed by specific organs within your body and they're used to diagnose disease. Okay, we call them tracers because we can trace the flow of these isotopes through your body and we can visualize them through imaging. Now the key thing here is that they are non-ionizing, which means they're not going to create those dangerous free ions in our bodies, and they also have really short half-lives, which means they are going to decay very, very quickly, and they're not just going to be hanging around in your body, providing another source of like background radiation. So here we have technetium-99. That's a very common radioactive isotope that we can use in medical imaging. Iodine-131 is using for detecting cancerous cells in your thyroid. We can also use these radioactive tracers in agriculture, okay? We can use radioactive phosphorus to study plant growth because plants uptake phosphorus, right? We can put radioactive tracers in groundwater to monitor the path of industrial pollutants potentially as well. But we are seeing and visualizing movement through time, which can give us more information about stuff, which is always good, right? So phosphorus-32, it's injected into plants and we can track the flow of nutrients, which is important when we're looking at agriculture and growth patterns in crops, okay? I also can put radioactive tracers into liquid in a pipe and see if there is a leak anywhere, because I will pick up greater levels of radiation in where the place where it is leaking out, which is really cool. So there's lots of ways that nuclear chemistry can be used for good, but that is going to end it for our unit on nuclear chemistry, and it's going to end it for this year for chemistry. So lab closed, we're gone, fission.